Hello everyone, I welcome you all again for the interaction session on Experimental Physics 1. This course is being followed by NPTEL in July 2023 session. Myself, Vivekananda Naik, I am a Prime Minister Research Fellowship, a PhD Research Scholar at Department of Energy Science and Engineering, IIT Delhi. So let's start with today's session. So in today's session, we'll discuss about the time constant of an RC circuit and how the method of charging and discharging is used to measure the time constant and what do you mean by time constant, all these things. Then there will be discussion regarding the magnetic field along the axis of a circular coil. Also there are some special cases also there are some special cases using which we can calculate the magnetic field at the center of the circular coil, and other cases also we can calculate. And in the third experiment we will discuss about the induced EMF in an coil. So let's start today's session. So now talking about RC circuit, like in LC circuit we have already discussed. In case of LC circuit, an inductor and a resistor are connected in series and they are connected to a power supply or source. So similarly in case of RC circuit, a capacitor and a resistor is connected in series, and as you can see, as it can be seen from the figure, you can clearly see there is a power supply. This power supply is this Vs, suppose. Now if you up now this is the power supply, so the positive terminal is here, so current will flow in this way. So this is the direction of current. Now if this current is I, then if you put Kirchhoff's law here, Kirchhoff's voltage law, Kirchhoff's voltage law, then what you will get, this Vs will be equal to, now the total voltage Vs will be voltage drop across this resistor and voltage drop across this capacitor. Now the voltage drop across the resistor is VR, plus the voltage drop across the capacitor is Vc. Now the voltage across the resistor we know is V is equals to IR, so I is the current and R is the resistance, then plus, and for capacitor we know V is equals to Q by C, where Q is the charge stored in the capacitor, because we know capacitor is used to store electric charge. So we know uh, I is equal to dq by dt. So if you put this in this equation, then we can get dq by dt into R plus q by c equal to Vs. So if you rearrange all these equations, then we can get dq by cVs minus q is equals to 1 by Rc into dt, is not it? So if you take integration on both the sides, it will be 0 to q, because initially there is no charge in the capacitor, and after certain time t, the charge stored in the capacitor is q. So here for time it will be 0 to t. So if you solve this, you will get ln cVs minus q divided by cVs is equals to minus t by Rc. So if you take exponential on both the sides, then this logarithm will cancel out. So there will be q. Q will be cVs 1 minus e to the power minus t by Rc. So this is the charge, which is a function of time. With time, the capacitor will get charged. Then for current, this I is equal to dq by dt. So we get I is equals to V by R or Vs by R 1 minus sorry, it will be only exponential minus T by RC. Now, if you see, now this is the case of current and this is the case of charge that varies when when the capacitor and the resistor are connected in series. Now, let us consider the case of how the charging and discharging is used to measure the time constant. Now, what do you mean by time constant? Now, this is this RC, the product RC is called as time constant, and if you see the unit of RC is also, I mean the dimension of RC is also equal to the dimension of time, because R is resistance and C is Q by V. So if you put all this, then you get RC has the same unit as the other time. So it how it basically what it represents. Now if you see here, if Q is equals to CVS. Now suppose this CVS is the charge which it will store after sufficient amount of time. Suppose this is the Q infinity, that is after some sufficient amount of time, or this is the maximum charge that can be stored in the capacitor in this circuit. So 1 minus e to the power minus t by RC. So if you put here RC equals to, so now here T, if you put T equals to RC, then what you will get? It will, Q will be Q infinity 1 minus 1 by E. So also this is the case of charging. Now if you consider the case of discharging, then the relation will be different. So now in order to consider the charging and discharging case, we can take the help of this circuit. Now this circuit you can see there is a voltage source connected here, and there is a resistor in series, and the capacitor is also in series with the resistor. But here there are two terminals A and B. So when we connect the terminal, this terminal to A, then the current will flow in this way. There will be no current in the B branch. So the capacitor will get charged up. Now in case of charging, like we solved recently. So in case of charging, what will happen? In case of charging, this charge Q will be given by the relation Q infinite, that is after sufficient number of amount of time, what is the charge? Then 1 minus e to the power minus t by RC. If you can clearly see, if you put infinity here, then Q will be Q infinity. So this is the Q infinity, the total, maximum charge that can be stored in the capacitor. Now the current will be I0 e to the power minus t by RC. Now this RC is called as time constant. Time constant, which is represented by tau also. And again, if you consider about voltage, because V is equals to IR. So if you consider about voltage, then the voltage will be having the same form of or same type of variation. V will be V infinity 1 minus e to the power minus t by tau, which is for capacitor. Now in case of discharge, so how will the discharging circuit behave? Now when you connect it on terminal A, then the current flows from first the current goes through resistor and then it goes through capacitor. But and the nature of the charging is shown here. But when you disconnect this from the point A and you connect it to the point B, then there will current flow in this loop only. There will be no current in this area because it is disconnected from here. Now there is no source in the initially when it was connected to A, there was a source, the source of voltage which was supplying current to the circuit. But here, as you can see, when there is when the connection is with V, there are no voltage sources here. But however, since the capacitor is charged, then the capacitor will drive the circuit by discharging. So when the capacitor drives the circuit, as you can see, the current initially the current was flowing in this way, but when the capacitor discharges, the current will flow in the opposite direction, and this capacitor will act as a source of voltage. So in that case, what will be the charge in the capacitor? The capacitor will get discharged. So this will be Q0. Q0 means initially charge that was stored in the capacitor at a given time, because we know capacitor can store charge. So at t is equal to 0, suppose capacitor had charge Q0, because only if it has some charge, it will drive the circuit by discharging it. So it will be Q0 e to the power minus t by tau. Similarly, current will remain same, because as you can clearly see, this current is but the direction of current is opposite. So the current direction will be opposite, and the voltage similarly, voltage will be V is equal to V0 e to the power minus t by tau. So it is the case of discharging case. Now, what do we mean by the time constant? Now, if you see, now this is the graph which represents the variation of charge versus time for capacitor and variation of current versus time for resistor. And similarly, it is the voltage versus time for capacitor and voltage versus time for resistor. Now, as you can clearly see, like we saw, the when the when the capacitor is charging, then it will increase exponentially. Similarly, the current will fall exponentially, because as you can clearly see from this relation, it is I0 e to the power minus t by RC. So the current for a resistor will current for a resistor will drop. Since the current is dropping and the resistance value remains constant, so the voltage will also follow the same trend. However, in case of capacitor, since it is charging, so the voltage will be increasing. So now, how to calculate what is the time constant? Now, if you see, if T is equals to RC, then Q will be how much? Q will be Q infinity, Q infinity 1 minus 1 by E. We know 1 by E is nearly equal to 0.37. So 1 minus 1 by U will be, suppose Q is equals to Q into, since 0.37, 1 minus 0.37 will be 0.63. So this will be the charge. So the time when the capacitor is when the capacitor charging, because I discussed this for the charging case 1 minus 1 by E. So when the capacitor is charging, the time constant is defined as the time required to charge the capacitor up to 0 or 63% of his maximum charging capacity. Or if you consider the case of discharging, then in case of discharging, this is the case of charging, but in case of discharging, it will fall like that. So in Q will be Q0 into 1 by E when T is equals to RC. So it is the time which the capacitor takes to discharge by 37% of its maximum capacity or initial capacity. So Q is equal to 37% of initial capacity. So this is defined as the time constant. So now these are the few concepts regarding related to the time constant of an RC circuit. Now let's consider the second experiment. Now this is how to calculate the magnetic field along the axis of a circular coil. Now we know there is a law in the magnetostatics which is known as Biot-Savart's law, and it gives the value and direction of the magnetic field for a coil carrying, for any portion of the coil carrying current. So if you are measuring at a point P which is at a distance R from that current element which is carrying current, and it will produce magnetic field, because we know current carrying conductor produces magnetic field. So this is the, if dl be the length of the coil, then and I is the current flowing through that coil, then according to Biot-Savart's law, the magnetic field generated at distance R is dB is equal to mu 0 by 4 pi I dl vector cross R vector by R cube. Or if you write it here, only the magnitude, it will be mu 0 by 4 pi I dl sine theta by R square, because R will get cancelled out and there will be sine theta from this cross product value. Since we are considering only magnitude, so there are no direction associated here. Now if you apply the same thing with respect to this circular coil carrying current, now you can see, suppose we consider these two elements. When you consider these two elements, now there will be component of magnetic field in x direction. Suppose this is the x direction and this is the y direction. So suppose this is the angle phi which it makes, this solid angle portion, this phi it makes with this central axis and the point that connects the small portion we have considered of the coil. Then if you this is the resultant magnetic field due to this component dl, then When you dissociate it into x component of y component, it will be dB sin theta and dB sin phi and dB cos phi. Now similarly for this component also there will be dB cos phi and dB sin phi. So as you can clearly see, these two components cancels each other. So there will be only dB sin phi. The resultant will be dB sin phi for each component. Like here there are two components, so it will be dB sin phi into 2. So the total magnetic, so the magnetic field, small person, if you apply this formula, it will be how much? You know, IDL sin theta by r square into mu 0 by 4 pi. Now here in this case, theta is equals to 90 degree, because this we have considered the current is flowing. The angle between the length vector and the position vector of this point is 90 degrees. So if you put this value, so the magnetic field B will be dB sin phi integration. So this dB is this much. So it will be mu 0 by 4 pi I dl by the distance. The distance is will be how much? A square plus x square sin phi. Now this sin phi, if you calculate, the sin phi will be how much? Sin phi will be a by a square plus a by x square plus a square square root. So if you put this, then b will be mu 0 by 4 pi. So if you put this an integration, this dl will be 2 pi. This is a. So total it will be 2 pi r. Integration of dl, l will be 2 pi r. So if you put all this, you will get mu 0 I a square divided by mu 0 I a square divided by 2 a square plus x square to the power 3 by 2. This is 1 x square plus a square to the 1, and this is in sin phi there is a square root factor, so it will total give us 3 by 2, and then this is there is one a here sin phi and another a will come from this 2 pi r. So this 4 pi 2 pi will get cancelled out and only 2 will remain in the denominator. So this is the magnitude of the magnetic field that is produced. Sorry, this is the magnitude of the magnetic field that is produced. So again, if you consider, suppose there are n number of turns, then what will be the magnetic field along the axis? It will be mu 0 n I a square divided by 2 a square plus x square to the power 3 by 2. Now, if you see this formula, the maximum value of magnetic field is achieved at x equal to 0. So if you suppose this is 0, x is in this direction, and in this axis there is magnetic field B. So it will be like this. So the maximum value of magnetic field here, suppose this is B0. Now what will be B0? Now B0, if you see here, B0 is at x equal to 0. So when you put x equal to 0, then what we will get at x equal to 0, B will be B0, which is mu 0 by mu 0 n I by 2aq into a square, because this a square 3 by 2 cancel out to give us aq, and this x is 0. So it will be mu 0 n I by 2a. So as you know, this is simply the magnetic field of a circular coil at the center of the circular coil. Now, if you consider about the direction, then the direction of the magnetic field can be given from this right hand thumb rule. If you curve your fingers, then if the direction of the rotation of the finger give the direction of the magnetic field, then the current direction will be given by the right hand thumb. So this is basically related to the direction. Now if you consider similarly, in this case also, with change in magnetic field, the current will be different, or with change in current, the magnetic field produced will be in different direction. So these are the few things related to um, the magnetic field along the axis of a circular coil carrying conductor. Then now we know about electromagnetic induction. According to electromagnetic induction, whenever there is a flux linked with a coil changes, then there is a current that flows inside the coil, and due to this current, there is an EMF which is induced in the circuit, or induced in the coil. So there will be current flowing in the coil. So now you can see, when this north pole of the magnet approaches this coil, then the magnetic lines of force, the value of the magnetic lines of force changes, because as it goes close to, we know, the suppose this is a magnetic pole, so the magnetic lines of force go in this way. So if you see here, the magnetic field B1, and here the magnetic field B2, so it is clear that B2 is less than B1. So when you go closer and closer, the magnetic field changes. So we know flux is related to the magnetic field, because phi is equals to B into A. So the flux also changes. Now due to this change in flux, there is an EMF which is induced, and that EMF is given by the formula small is equal to minus d phi by dt. If the coil has number of turns L, then it will minus n d phi by dt. So this is the formula for EMF. Now, how the negative sign comes? The negative sign comes due to Lenz's law, and it says the Lenz's law is in accordance to the conservation of energy, because it is changing. So, what the Lenz's law states? The Lenz's law states that the magnetic field which results in the flow of current in a coil. Now the direction of the magnetic field which is already present here, and the direction of magnetic field which will come as a result of the current flowing in the coil, they will be in opposite direction to each other, or it will oppose the magnetic or change in magnetic field. So suppose if you are taking a north pole towards the coil, so the magnetic field will the current will induced in the circuit in such a way that the face of the coil which is towards this magnetic pole, it will be again north pole. So it will repel each other. That is, it will try to reduce the effect of that magnetic field which is resulting in production of that induced EMF. So this is the uh, um, so now if you consider about the solenoid, then we know in case of a solenoid, the magnetic field inside solenoid is given by mu 0 Ni by L, magnetic field induced per unit length. This is the length L. N I is the current flowing through the solenoid. N is the number of turns, and mu 0 we know, mu 0 is 4 pi into 10 to the power minus 7. This is the magnetic permeability of the medium. So the but if you apply here alternating current, then it will be mu 0 N by L. If you current is changing sinusoidal, it will be 2 pi ft, like that. So these are a few things related to the electromagnetic induction, and this electromagnetic induction, it is according to the Lenz law, and according to Lenz law, it is the magnetic field produced due to the change in due to the flow of current in the coil will oppose the existing magnetic field which creates it. So now let's solve a few questions related to these experiments or these concepts. So the question is, an air core solenoid of self-inductance L has n turns of fine insulated copper wire, and area cross section of the solenoid is A. If the area and the number of turns are doubled, and the core is filled with a medium of relative permeability 1000, then the self inductance of the coil will be how much? So the question says there is a solenoid. Now the solenoid is like that, number of turns, there are n number of turns. So the there are n number of turns and its self inductance is L. And the area of cross section, this area of cross section is A. This area of cross section is A. Now, when question says the number of turns are doubled, the number of turns are doubled. Now this n changes to 2n and the core is filled with a medium of relative permeability 1000. Now there is a air cool. For air cool, it is 1, but for this but for the core which was filled, the relative permeability is 1000. So the mu, which is the relative permeability, is 1000. Now, what will be the new self inductance of the coil that will be produced as a result of this changes? So I will request you to try this question, or after a few minutes we will discuss. So let's solve the question. Now the self-inductance of the coil. The self-inductance of the coil is given in terms of this permeability of the core, area, and number of turns divided. Number of turns is the self-inductance of the coil per unit length is mu0 A n square divided by length of the coil. It is given, the self-inductance of the coil is given by mu A n square divided by the length of the coil. Now the permeability initially the relative permeability 1. Now this mu will be how much? 1000 because it was changed to core was filled with a medium of relative permeability 1000. Then the area of the cross section was same, but if the area and the number of turns are double, sorry. So if the area are also doubled, so area will be 2 times. So it will be 2 into number of turns are also double. So it will be 2 square. So it will be 8000 L. So the new self-inductance of the coil will be 8000 L. So when you fill a core inside the solenoid and it has the relative permeability of 1000, and if you double the area and double the number of turns, then according to the relation, because they are directly proportional to the self-inductance of the coil is directly proportional to the area cross section and directly proportional to the square of number of turns of the solenoid, not of the coils of the numbers of turns of the coil. So the new self-inductance will be 8000 L. So the next question. The question says a straight air core solenoid has a length 1 meter, area cross section is 10 centimeter square, and total number of turns is 2000. If a current 1 ampere is flowing in it in flowing in it is reversed in 0.1 second, then the average EMF induced in it will be nearly how many volts? So the option is A 10 volt, B 1 volt, C 0.1 volt, or D 0.5 volt. So there is a solenoid and the core is made up of air. So there is no core, only air. The length of the coil is 1 meter and the area cross section of the coil is 10 centimeter square, and the total number of turns is 2000, and the current flowing through the circuit changes in 0.1 second. So the average EMF which will be produced will be nearly equal to how much? So I request you to try this question. Then after a few minutes we will solve. Yes, can anyone tell me what will be the average EMF that will be induced in the solenoid? So we just discussed that the self-inductance of the coil is given by L is equals to mu 0 N square A by L. Sorry, mu 0 N square. This is the per unit length. So total solenoid will be into L. This is the length. Suppose it is small L. Then uh, the EMF induced is given by the induced EMF. The induced EMF is given by is equals to minus L di by dt. So this is the change in current with respect to time. Now, if you can calculate L, then we can direct put the value of L to get the value. Put the value of L to get the value of the induced EMF. So this induced EMF U will be minus sign is due to the Lenz's law, which is negative. Now mu 0. Mu 0 is 4 pi into 10 to the power minus 7 into n square. N is 2000 number of turns of the coil, 2000 square into area is 10 centimeter square. 10 into, if you convert centimeter square into meter square, it will be 10 to the power minus 4 multiplied with it into area plus then length is 1 meter. Length is 1 meter divided by, sorry, into, this is di by dt. Now the change in current divided per time. Now it is given here the current of 1 ampere flowing in it is reversed in 0.1 second. So the current reverse means initially it was 1 ampere, the direction was changed. Then similarly it is again 1 ampere. So 1 ampere current was flowing in this plus x direction, but in 0.1 second the current started flowing in minus x direction. So the change in current will be how much? It will be initial minus final minus 1 divided by 0.1. So it will be 2 by 0.1. So here it will be, in place of di by dt, we can write 2 divided by 0.1. So here we can write 2 divided by 0.1. So if you solve it, it will give you 0.1 volt approximately. The value will be 0.1 volt. So the correct option is option C, which is 0.1 volt. So now there is a trick in this question that the current 1 ampere flowing is reversed. So the 1 ampere current was reversed means the direction changed exactly opposite to the initial direction. So 1 ampere changed to minus 1 ampere. So the total change in current is 2 ampere. Since we are considering only change in current, so there will be 2 ampere. There will be no sign like if you change minus 1 of minus 1, then it will be minus 2. But here there is only change in, we are taking the magnitude of change in current with respect to time. So it will be 2 by the time is 0.1 second. So this will be the induced EMF, which is 0.1 volt. Now the third question says a plain square loop of thin copper wire has 100 turns. Each side of the loop is 10 centimeter long and the loop is oriented with its surface making an angle of 30 degree with a uniform magnetic field of flux density 0.4 Tesla. If the loop is rotated in 0.5 second so as to orient its surface at right angles to the magnetic field, what will be the magnitude of the average EMF induced in the loop? So this is a very good question. The question says there is a loop of thin copper wire and the side of the loop is 10 centimeter long. So suppose this is the loop of copper wire. This side is 10 centimeter. So this side is 10 centimeter and the loop is oriented and its surface is making an angle 30 degree with a uniform magnetic field of flux density 0.4 Tesla. So at a particular situation, it is oriented in such a way that suppose this is the direction of magnetic field, it is oriented in this way. Suppose it is oriented like this. So this is the angle which is how much? Which is theta. And this theta is 30 degrees. So it makes an angle 30 degree initially. The initial condition which is given, it makes an angle 30 degree. Now, if the loop is rotated in 0.5 seconds so as to orient its surface at right angle to the magnetic field. Now, this is so it gets oriented. Its surface is at right angle to the magnetic field. Suppose the surface is like that. That is, this angle is 90 degree. So in this, it was the first case when it was 30 degree. Then it gets oriented to here, and the angle in second case this angle is 90 degree. Now, what will be the magnitude of the average EMF that will be induced in the coil? Because as you can clearly see, since there is some angle and there is BA cos theta, you must be remembering the magnetic flux. So this is the case. So you need to, since the angle is changing, so the flux will also change, and due to this change in flux, there will be a induced EMF. So we need to calculate what will be the value of the induced EMF in the coil. So I'll give you a few minutes to try this question, then I will solve it for you. So let's solve this question. Now we know the EMF induced is V equals to minus d phi by dt. So this is the EMF. Now we need to find out the change in EMF when the coil gets rotated from theta is equal to 30 degree to theta is equal to 90 degree. So the now if you see the loop is rotated in 0.5 second and to orient its surface at right angle to the magnetic field. Now you know the if you see, suppose this is the circular loop. Now the area vector will be perpendicular to this plane. So if in this case this theta is equal to 30 degree means the area is perpendicular to this surface. So this angle will be how much? Total is 90 degree. This is 30 degree. So this will be 60 degree. So initially in initial the angle between the area vector and because for flux is b dot a vector, that is ba cos theta, b vector dot a vector. So for first case when the angle is 30 degree between the magnetic flux and the surface, then since the surface area vector is perpendicular to the surface, the angle between this magnetic field and the surface will be 60 degree. And in the second case when it is perpendicular, so the area vector will be along the direction of magnetic field, so theta will be 0 degree. So this is the most important part of this question. So now we will calculate the magnetic field. Now here if you see in 0.5 second the magnetic field strength will be 0.4 Tesla. So in first case magnetic field is 0.4 Tesla. So phi 1 will be how much? VA cos theta. Now here it is given the coil has 100 turns. So it will be NBA cos theta. So for first case N will be 100 into 100 N is 100 into 0.4 Tesla into A is 10 centimeter. 10 centimeter into 10 centimeter is 10 centimeter 0.1 meter. So it will be area will be 0.1 square into cos theta. Cos 60 is how much? 1 by 2. This 1 by 2 represents cos 60 degree. So the so if you calculate it will be how much? 100 and 0.4, 0.1 square is 0.01 by 2. So it will be 0.2 Weber. So this is the case. First case is 0.2 Weber. Now for second case, now the first case phi 1 is 0.2 Weber. Now for second case, it is cos 0. Cos 0 is 1. It will be 0.4 into 100 into only all the part will remain same, but there was only half here. It will be 1. So it will be 2 times of that. So it will be 0.4 Weber. So what is the change? Change is phi 2 minus phi 1 is 0.4 minus 0.2 equal to 0.2 Weber. Now this is 0.2 Weber. The flux change is 0.2 Weber. Now the time taken is 0.5 seconds. So the time taken delta t is 0.5 second. So we know EMF is minus d phi by dt. So it will be 0.2 divided by 0.5, which will give us 0.4 volt. Isn't it? So the EMF induced in the coil is 0.4 volt. So the question is the calculation is very simple, but only concept hidden here is the angle between the magnetic field and the coil, because we know the magnetic field is in a particular direction, but the rotation due to the rotation of the coil, the area vector which is perpendicular to the plane of the coil is changing. So when it is given that the surface makes an angle 30 degree, means the area vector is which is perpendicular to surface, it makes an angle 60 degree. There will be 90 minus 30. So when the resultant or the final position is perpendicular to the magnetic field, then the area vector will be along the magnetic field, because the area vector is perpendicular to the plane of the coil. So this is the trick. So in first case, we calculated the magnetic field strength is 0.4 Tesla. So the magnetic flux is 0.2 Weber, because cos 60 is 1 by 2. But here, since cos 0 is 0, sorry, cos 0 is 1, cos 90 is 0, cos 0 is 1. So here we calculated it is 0.4 Weber. So the change is 0.4 minus 0.2, 0.2 Weber, and the change was attained in a time period of 0.5 second. So the EMF induced will be 0.4 volt. So the correct option will be option C, 0.4 volt. So these are the three questions we discussed today. So I will take another session tomorrow, which will be of 2 hours. This was an extra session for 1 hour from 7 to 8 p.m. So tomorrow we'll discuss some other problems, and we will try to solve the last week problems, which are based on some other concepts. So I would like to stop here. So that's it for today. We'll meet again tomorrow. Thank you for joining in today's session.